So let us quickly try to understand how this can be generated. I'll take the original carrier in the form of cosine function. I will have to somehow convert cos into sine because in the second term carrier is present in the sine form, which can be done by passing this cosine function through 90-degree phase shifter. So we get sine form of the carrier. I'll have to multiply sine form of the carrier with phi of t, and please do not forget that phi of t is nothing but 2 pi kf, which is a constant part, but more than that it is integration of modulating signal. So we will need an integrator through which we will pass the modulating signal. So now before we look at the block diagram, I want you to visualize the block diagram. We have modulating signal, it will pass through the integrator. Output of the integrator will be multiplied with sine form of the carrier. For multiplication, what we use is nothing but balanced modulator or product modulator. To get sine form, we will pass the original carrier through 90-degree phase shifter. And to generate the original carrier itself, we may have crystal oscillator and buffer amplifier. Finally, these two paths will be added with the help of an adder. The output will be narrowband FM, which will be later on passed through multipliers and mixers. Let us have a look at the block diagram. So let us continue. This is the block diagram of Armstrong's method that we are discussing. It's an indirect method to generate FM signal. And we have already done one mathematical analysis which you have to remember. So you can see we are applying modulating signal which is m of t in our case from this side. There is integrator equalizer, which in simple words is an integrator. So output of this will be nothing but integration of m of t with respect to time. So we are applying modulating signal from this side to the integrator equalizer, which is in simple words nothing but an integrator. So output of it will be nothing but the integration of modulating signal with respect to time. If you remember, we have to now generate the sine form of the original carrier. So you can see we have a crystal oscillator, generates the carrier, and buffer amplifier is used to increase the output current drive and also to provide impedance matching. So output of buffer amplifier will be nothing but my carrier in the form of cos 2 pi fct. And you can see it is given to 90-degree phase shifter. So here you have 90-degree phase shifted carrier, and the 90-degree phase shifted carrier will be nothing but sine 2 pi fct. So this 90-degree phase shifted carrier and integration of m of t are multiplied by product modulator. So this particular point x, at point x we will have this signal 2 pi kf. This is the constant that will be added to the integration. Integration will be m of tau d tau from 0 to t. Mathematically it will be from minus infinity. This was nothing but our phi of t, and this will be multiplied by sine 2 pi fct. No doubt that amplitude of sine, which is in the form of vc, will also remain. And that gets added to the original form of cosine, which is available at the output of buffer amplifier. Obviously, to preserve that sign of plus and minus, we will use adder with inverting amplitude. So S1t in terms of the notation that we have used. So output of the adder will be nothing but VFMT, the expression that we have derived before. And please remember that this VFMT is nothing but narrow band FM because we had assumed the value of phase phi of t to be very small. Now narrow band FM means mu f is small, modulation index is small, and it also means that delta f is small, the frequency deviation is small. That means the bandwidth of the signal is also very small. You can see it is passed through the multipliers, mixtures, and then again multipliers. Whenever we have multiplier will increase the value of mu f as well as delta f both. But here every new carrier frequency will be multiplied by that scaling factor. Mixture will give us a specific frequency of the carrier. Mixture requires two values. We have discussed this before. The second frequency will be the output of another oscillator, crystal oscillator. So when it passes through mixture, delta f will not change. If you remember, delta f remains same because every frequency gets incremented by the same amount. And if delta f remains same, mu f also remains same. So basically what we change when the signal passes through mixer is the carrier frequency. We again passing through multiplier to further increase mu f and delta f, and finally what I get is my wide band FM. So that's nothing but the block diagram, and with the help of mathematical analysis, one can easily explain the Armstrong method. One more part that can be added to the Armstrong method is the phasor diagram. So let's quickly go through the phasor diagram, which will be nothing but the phasors of various signal that we have in Armstrong's method.